I know we've been talking about these gas laws, and I keep seeing a lot of stuff in the comments about the ideal gas law. Now, yeah, let me say something about the ideal gas law. Oh, you're welcome, Jen. So, with the ideal gas law, right, we've been working with a lot of variables. But let me tell you all how the ideal gas law, because a lot of those other gas laws tend to look the same, right? But here's something else that kind of throws students off a little bit. With the ideal gas law, it's PV equals nRT. Perv nerd, okay? I forgot what somebody said earlier yesterday. They had another little mnemonic that they used. But with the ideal gas law, I tell students that if you write down the formula, you should actually derive all the other formulas out of the one. So in other words, if I'm looking for pressure, right, it's going to equal to nRT divided by V. If I'm looking for volume, it's nRT over P. See that? See that? I mean, they look the same. I just swapped them. That's all. I just swapped them. If I'm looking for N, the number of moles, now here's where it changes up a little bit, right? N is equal to PV divided by RT. And if I'm looking for the temperature, again, it's PV over NR or RN. I'm going to say RN since many of you guys are wanting to become nurses, okay? So let's keep that same vibration, RN, all right? So if you see these formulas right here, I recommend that you write them down on index cards so that you are familiar with the way they should look, okay? And those moles are back. So we talked about moles about a month ago. And with the R, because you don't have to really look for the R, that is the gas constant. You're going to be given all 4 of the 5 numbers that you're solving for, okay? You will be given that. So for this particular problem right here, let's read it, and then we're going to plug in the formula that we need. A hospital oxygen cylinder has a volume of 10.0 liters and is filled to a pressure of 140 atms at 22 degrees Celsius. You know you need to convert those degrees Celsius to Kelvin. How many moles of oxygen are contained in the tank? And here is your gas constant that you're going to use for this problem. So what I'm going to do is plug in everything that we're solving for right here. So we're looking for N, the moles, right? So to make this easier, let me see. Hold on, y'all. I'm going to scoot that down. Yeah. Scoot it down. Your N is equal to pressure times volume divided by your gas constant times your temperature. Now, due to the space, let me go ahead and do it right here. 22 degrees Celsius, add 273 to that number. All right. So that way you are able to get your answers. That's equal to 295. And if we wanted to add the 0.15 on there, because again, Kelvin is 273.15, I'm just going to work with 295, okay? Just for the sake of using some whole numbers here. All right. Now, 273, Elizabeth. Yep, 273. So the pressure that they gave us was 140 atm. The volume that they gave us was 10.0 liters. We're going to divide that by the gas constant. That's 0.0821 liters dot atm per mole dot Kelvin. Those are the units for your gas constant. Times your temperature. You're good, honey. You're good. Times your temperature, 295 Kelvin. Now, what you're going to do, you're going to cancel out your ATMs, cancel out your liters, cancel out your Kelvin, And just like that, you're left with a mole. Okay? You're left with your moles. So let's plug this into our calculator so we can see the correct answer. 140 times 10.0 divided by 0.0821 and divide that again by 295 and you get 57.8. 57.8. Now let me tell y'all a little secret. Moles of oxygen. If I wanted to have you all do something extra to this problem, I could very well say, give me my answer in grams. How many grams of oxygen? And in order to find the grams, you need the molar mass of O2, which is 32.00 grams. All right? How did I get that? Because 2 times 16 gives you that. You can, but I just plug it all into the calculator at one time. So, yes, you can say 0.0821 times 295, but rather than separating them, I just went ahead and plugged these two top numbers in, then I divided it by the bottom numbers. You can do it both ways, okay? You can do it both ways. Yes, so just so you see it, all right? 140 times 10.0, that gives us 1,400. You're welcome. I'm going to write this number off to the side, and it's going to be small, but I'm going to write it over here. We get 1,400 for the top number. Now, for that bottom number, 0.0821 times 295, we get 24.2. Because we're rounding off to 3 sig figs. So now, if you plug that in, 1,400 divided by 24.2, you're going to still get the 57.8, which is what we got right here. Now, here is the other thing. If I told you all to give me my answer in grams, then you would say 57.8 moles of oxygen times 32.00 grams of oxygen, because remember, that's the molar mass, and we talked about that a few weeks ago. You're going to cancel out the moles, and just like that, 57.8 times 32.00 gives you 49.6, but we can roughly say 1850. Okay, if we want to keep 3 sig figs, see that 1849.6? You would round it off to 1850, and that's giving you your 3 significant digits. So if I told you, okay, for 3 sig figs, it will be 1850 without the decimal grams of oxygen. If I asked you to do that, if you think about the ideal gas law, y'all, they're going to give you 4 of your 5 numbers, okay? 4 of your 5 numbers. So again, do not hesitate when it comes to those ideal gas laws, okay? Do not. Now, if you look at number 3 right here, okay, it says a body discovered in a sealed 50-liter container has produced 1.2 moles of methane gas due to decomposition. Whew. If the internal pressure of the container is measured at 1.1 atm, what is the temperature inside the container in Celsius? Now, I'm interested to see this one, okay? Remember, this is the ideal gas law. However, because they said, what is the answer in Celsius? First, you need to put it in Kelvin. Then you're going to get the answer in degrees Celsius by subtracting, okay? I'll tell you what to do when we get to that part. So since you're looking for temperature, let's highlight what we know. 50 liters is your volume. 1.2 moles is your N. 1.1 atm is your pressure. The gas constant was that 0.0821 variable. So you're looking for your T for temperature. So let's rearrange the formula to solve for T. T equals P times V divided by Rn, okay? So here is my first thing. The pressure was 1.1 atm. The volume was 50 liters. The R, the gas constant, 0.0821 liters dot atm per. Now, this is not a number that you all should memorize. This is a number that your teachers will give you on your test. That's not something you would need to memorize. Times 1.2 moles. All right, let's get rid of the units we do not need. We don't need atm. We don't need liters. We don't need moles. We were solving for Kelvin. So let's plug this into our calculator. 1.1 times 50 divided by 0.0821, and then divide that by 1.2, and you get 558. Yeah, that's really hot, okay? So my temperature is 558 Kelvin, but in order to get that into degrees Celsius, because that's what they were asking us to do, okay? Let me show you all the formula. Kelvin is this right here. But if you're looking for degrees Celsius, you subtract 273 from the number, okay? So to get your degrees Celsius, it would be Kelvin minus 273. So keep those two formulas in mind, all right? Keep those two formulas in mind. All right, so what you're going to do is you're going to plug this temperature right here in right here, okay? Because we got to find it in degrees Celsius. So the temperature that we just got was 558. So since we're looking for degrees Celsius, 558 minus 273. Let's plug it in so y'all can see that. 285 degrees Celsius is our answer. All right. Any questions about what I did? Okay, yes, here's Dalton's. Now, y'all, Dalton's is just saying add those numbers, okay? Add them up. So whenever you give, it's the total pressure, okay, of gas mixed. It's the total partial pressure of gas that's mixed in a container, a chamber, or whatever the case may be, all right? So in this particular example right here, if you're dealing with Dalton's law of partial pressure, you're just adding all the gases.